Okay, so we were back here trying to build that group with the yes, with the extra thing. Yeah, yeah, with the extra with the exponent constraint. Did I interrupt this? I don't know. I don't remember. But yeah, let's. Give me another recap of what the 1 plus 2 exponent meant, please, for P groups. It highlights a specific structure. So P is a prime and N is a positive integer. The 1 refers to the order of the center, which is exactly P, minimal for non-abelian P groups of this type. The 1 refers to the order of the center. So okay, but maybe it's just because it's p to the power of 1. Not sure I understand why we need to mention the order of the center being 1. Is there group definitions that look like 2 plus 2n, for example, as an exponent? Like, is it just the 1 always there? You know what I mean? Like, the 1 refers to the order of the center. Yeah, n plus 2n, that's maybe a better way. And then 2n indicates the even exponent in the order of the quotient g over zg. Okay, so the quotient of, let's think about this. So we've got g. If we do the quotient with the center, and that was again doing the modulo stuff, right? Symplectic form with the commutator map, making these groups key in classification and extensions. With center order P and quotient Z over PZ squared. So the 1 in the notation 1 plus 2n for special groups refers to exponent of to the exponent on P for the order of the center. Yeah, okay, cool. Not a literal order of 1. An order 1 center would be trivial, implying group is abelian, which contradicts an abelian. Yeah, the reason the center order is explicitly mentioned in the highlight in the notation as 1 is that its core defining property of extra P groups, the center is as small as possible, exactly order P, while ensuring the order is non-abelian, the group is non-abelian with the derived group. Okay. Regarding notations like 2 plus 2n, or more generally m plus 2n for P group orders, yes, similar breakdowns appear in literature for broader classes of P groups, though they are not always standardized, with the same emphasis as 1 plus 2n for extra special groups. For instance, special P groups, a superclass is only abelian of order Pm, but not necessarily m equals 1. So the total order is Pm plus k, where k is the rank of the element abelian quotient, and m, yeah, okay. Okay, yes. So it's rigidly fixed as 1 to n, but okay. Okay, so essentially that's kind of like a bit of a fixed notation thing. Generalizations m plus kn, where m is the center's exponent and kn reflects the quotient's dimension, but these are context specific in automorphisms. Okay, so they're very. So essentially, 1 is just telling us the center is as small as possible, and the order of the quotient is 2. Now let's say what that, let's try to understand what that means, right? The order of the quotient is, so how to construct these, right? Well, I guess we just construct it by just by just constructing it, right? I mean, the order of the quotient G over ZG. So with the quotient of the group with its center. Does this have any special meaning? So for a group G, that's the quotient group G over ZG have a special interpretation? Has. Maybe I could be using, maybe I can use the voice assistant for this type of questions. It would be cool if you had like a voice assistant that would be a mathematician. Wait a second. Voice mode. There's a, okay, it doesn't seem to work well, but let's just oh, now there's like some red stuff in here. Anyway, I wish I could just can I open it? Hey, are you there?
Hey, yes, I'm here. How can I help you today?
Yeah, there's no, you don't have a mathematician mode, right?
Right. I don't have a special mathematician mode, but I can still handle numbers and math questions pretty well. Want to toss me a math problem or something else?
No, I'm working on I'm working on something right now, but like don't just listen in, and then if I explicitly ask a question, answer, but if not, just don't answer. Okay, I'm talking out loud. It's not necessarily directed to you. I will ask you specific questions from time to time. I think that's gonna be.
Got it.
Yeah, cool. Okay, so I am looking at the special P groups. Okay, so I was looking at the interpretation of. So that's the recap. Sorry guys, for group G, that's the quotient group G over ZG has a special interpretation. Yes, the quotient group G over ZG as the center has a significant interpretation in group theory. It is isomorphic to the inner automorphism. It is isomorphic to the inner automorphism group. The inner automorphism group consists of all automorphisms of G that are induced by conjugation by elements of G.
Interesting. That's a key concept in group theory. If you have a specific question about it, just let me know, and I'll dive in with you.
Yeah, no, not yet. I'm just reading out loud just the grok answer in the chat. I'll ask you if I need it. Okay, just stay on the line. So isomorphism natural. Okay, so the quotient. No, just I'm muting you for now. I'll unmute you when. Yeah, but just keep listening. The isomorphism, the quotient. This quotient captures the non-commutative essence of G, as it measures how conjugations act on the group. If G over ZG is trivial, then G equals ZG. So G is abelian. Every element commutes with everything. Okay. Interesting. So if to say that it's trivial, what would it mean, right? I forgot how to compute that division, or the fact that it's G over, because I was just doing the mod thing, right? So So what would it mean for this quotient to be trivial? Can you explain me what it would mean for a quotient group to be trivial?
Sure. A trivial quotient group means that every element in the original group G is equivalent to the identity element under the quotient operation. So the quotient group G over ZG has only one element, the identity. In the case of G over ZG, where ZG is the center of the group G, the set of elements that commute with every element in G. If this quotient is trivial, it means G equals ZG, so every element in G is in its center, which implies that every element commutes with every other element. In other words, G is a billion, because for any A and B in G, A times B equals B times A. Does that make sense? Or do you want me to break it down further?
No, that makes sense, but I kind of forgot what's the process of calculating a quotient group. So how would you go about it? Like if I have G, a very simple group, and maybe you walk me through with a specific example. If I have like a group G and I want to do the quotient over its center.
Let's walk through a simple example. Suppose you have a group G that's the symmetric group S3, the group of permutations of 3 elements. It's got 6 elements, the identity, 2 3 cycles, and 3 2 cycles. First, we need to find the center, ZS3, the set of elements that commute with everything in S3. To find the center, take an element in S3 and check if it commutes with all others, meaning G times H equals H times G for all H in S3. The identity permutation clearly does this, so it's in ZS3. Now, check the 2 cycles, like 1 2. Conjugation of 1 2 by, say, 1 2 3 changes 1 2 into another 2 cycle, not itself, so 1 2 isn't in the center. Similarly, 3 cycles don't commute with 2 cycles under conjugation. After checking, you find only the identity commutes with everything, so ZS3 is just the identity element. Now, the quotient group S3 over ZS3 is S3 over the subgroup containing just the identity. In group theory, quotienting by the trivial subgroup, the one with only the identity, gives you back the whole group, because the cosets are just the elements of S3 itself.
Yeah.
So, S3 over ZS3 is isomorphic to S3, which has 6 elements. To compute the quotient generally, you, 1, identify the normal subgroup, here ZS3, which is normal since the center always is. 2, form cosets. For each G and G, the coset is G times
It's
ZS3.
okay. It's stop. It's actually hard to follow just on the voice. I think I need to read it. I just meant just what's the. Yeah, I think no. I'm gonna step back on this. I think the voice assistant doesn't work so well for these, or at least not something that I haven't thought of how to use.
No problem at all.
It's all good, baby. So let's go and do that thing where we just what are the steps to compute a quotient group? I think it was something like you were pairing the elements, and that was kind of you were pairing the elements, and then you're just focusing on that subgroup. But if essentially it gives you the same group, right? Yeah, the cosets, exactly. Yeah. Where G is a group and then is a subgroup of G. Follow these steps. The cosets GN are the left cosets Gn. So Gn such that n belongs to n for each G and G. So that's what you're doing. Yeah, exactly. With the cosets. But yeah, that was that was an equivalent to doing the modulo thing, right? Because you're kind of spreading. It's almost like you're nesting. Yeah, it's almost like you're nesting. Doing a G over n is like nesting n in G. So if G over Zg is trivial, then G equals Zg. But what does it mean? So what does it mean for a quotient group to be trivial? Does it mean that it's just this is what I don't understand? I think keep the answer short. It's okay. So trivial means it's only the identity. Okay. When n equals G. But why? How is that possible if you construct the quotient by looking at the cosets? So if n equals G, every element G satisfies the G equals G times E. Oh, okay. So it's so essentially all the cosets are isomorphic. That's what, and then essentially it's G. So Ng, then every element G satisfies this operation. So all cosets Gn collapse to a single coset. So it's so essentially all cosets are isomorphic with each other. I think that's what it means, right? There's only one coset, which is G. This is what I don't understand of the identity element. So if n equals G, then you're saying you know what I mean? The struggle that I'm having is that if you have this set of these elements, let's say 3 elements, and then you have another set with which is the same 3 elements. No, or then you divide it by, you do the quotient of the same thing, right? So you end up having these, let's say it's the same thing, but it's just red. Then you end up having these 3 points in here. These 3 points in here. You have these cosets, right? Where like this element is kind of multiplied or composed with each of them, right? But because it's the same, it just ends up being the same. These 3 cosets are isomorphic or are equivalent. I need to understand that. I know it's maybe not relevant to the problem, but it bothers me right now. Because it's the group theoretic sense. No. So if n equals G, then every element G satisfies that G equals G times the identity, and that belongs to Gn. So all cosets Gn collapse to a single coset. G itself, yes. So looking at your answer, looking at this answer of yours, wouldn't this mean that n over G, G over n equals G? The coset G itself acting as the identity. Oh, I know what you mean. Because it's the group. It's essentially now the elements are cosets, and so you just have one coset. This is what's very hard. So that I mean, because that's an abstraction. I know what it means. Okay, so because it's a set with just one element, then that's the identity. Yeah. Okay. Bro, this is yeah, that's a little mind bending actually. That's okay, that's all right, but I got it. So let's go back here. So the quotient. So what we're saying is, okay, so that's interesting, right? So that tells you, that quotient tells you how much. Yeah, okay, cool. So essentially, you just go back to practicality. So we're constructing a set P to the 1 plus 2n, and it's telling us 1 plus 2. That tells us that 2 is that the quotient has order 2, exactly. So so 3 to the power, to sum it up, 3 to the power of 1 plus 2 in theory would be a P group with a P group G with center ZG of order 3 and quotient G over ZG of order 2. This means that it has 2 elements, right? So it's not it's not the trivial one, so it's because it will be order 1 will be trivial. Exactly. So this means that it's not fully like everything commutative. Exactly. Does this make sense? That is just notation. Yes. And let's see if we can confirm these. No? Why not? Okay. No, somebody does not make sense. A key error in the quotient. So for expression P group G of order P1 with P equals 3 and N equals 1, the total order, that's okay. Total order is 27. The center ZG has order 3. That is correct. And the quotient G over the center has order P. Okay, has P order P2N. So P, so 3. Okay, so 9, not 2. Okay, fine. It's all good. This question is elementary abelian, isomorphic to Z over 3Z. The notation 1 plus 2 emphasizes the small center or B, and the even dimensional quotient over FP, whatever that means. Can you construct such group using SymPy, please? Oh, because I'm in expert mode all the time. I'll switch to auto. Okay, give me a second. I'm still recording. Cool. So, okay, I have that file here. Now what? Print the group order. Exponent. Let's run this. So SymPy can compute the exponent? Okay, error. That's what I was gonna say. go in expert mode maybe. Maybe I just, yeah. What's the, again, and what's the, so while it's fixing these, you're kidding me. Hold on. Yeah. Let's scroll down again or what? Grok, don't be down. So the meaning of that quotient with your own center is a measure of how much commutative you are and not. So it's exactly 9. How can it's just out of curiosity, right? Like how can you map constraints on the G over ZG quotient as rules in SymPy to build an instance of G? It actually is thinking, so I don't know why this one is not working. Ask Grok to fix, okay. Grok can't fix it. It's a runtime error. I think that is just it's on the runtime. It's not on the. Can you try again? From scratch with the SymPy code, please. Expert. Build a 3 to the power of 1 plus 2 group as described above, and here they're saying what is it thinking? So with relations, that's what I was meaning. So okay, interesting. I have no idea what is it thinking now, but no, it's unable to. Okay, then I'll have to stop it here until they fix that. But okay, hopefully I don't have to recap that again next time. But it's okay. Now I so that's just notation. It's the center, and then then there's a relation or constraint around the quotient. Cool. So this is basically what this means, and then we still have to do the plus sign in here, and then we can construct S, and once we construct S, we're going to do the rest. That's still going to take a few iterations. See you in the next video.